really deep into the world of physics with quantum field theory.
QFT.
Yeah, it sounds a little intimidating, I know.
Yeah.
But you actually don't need a PhD to get it, I promise.
Yeah.
So today, we're going to try to give you a solid grasp of the core ideas of QFT, what it is, why it matters, and how it's shaping our understanding of the universe.
Yeah. It's a real head trip.
We've got some pretty amazing source material to guide us today, and I promise by the end of this deep dive, you'll be dropping serious knowledge bombs at your next gathering.
Yeah, and it really does challenge our everyday intuition about, reality, what we think about reality.
The sources we've got for you today paint a picture of a universe that's not made of, solid objects, but of these invisible fields, just buzzing, constantly buzzing with energy.
Yeah. It's less billiard balls on a table and more like this vast interconnected ocean. Yeah. So quantum field theory, or QFT as it's known, is like this grand unifying theory in physics. And it bridges the gap between quantum mechanics, which, governs the microscopic world, and Einstein's special relativity, which deals with things that move really, really fast.
Right.
So it does this by introducing the concept of fields.
Okay, so fields. I'm picturing a magnetic field, but instead of attracting metal, it's creating particles.
Yeah, you're on the right track. Think of you're standing by a calm lake.
Okay.
The surface of the lake is like a field. Now, if you throw a pebble into the lake, you create ripples that spread out, right?
Right.
Those ripples are like particles. Yeah. They're disturbances in the underlying field.
So instead of thinking of a particle as a tiny little solid ball, we should think of them as these ripples, these excitations, and these invisible fields that are permeating everything.
Precisely. And it turns out that everything we see around us, from the air we breathe to the stars in the sky, is ultimately made up of these field excitations.
Wow, that's pretty wild. So we have these fields, and they're creating particles, but how do these particles, interact with each other? How do they create the forces that we experience? Like gravity or electromagnetism or all those?
Yeah, it's like playing a cosmic game of catch.
Ooh, okay, walk me through this. How does it actually work?
Let's take electromagnetism as an example. Yeah. You know how magnets can attract or repel each other?
Right, yeah.
Even without touching? They have this invisible force field.
Right.
So in QFT, we say that this force is mediated by the exchange of virtual photons. These virtual photons are like these temporary particles that just pop in and out of existence.
Okay.
And they carry that electromagnetic force between the charged particles.
So it's like the electrons and the magnets are tossing these virtual photons back and forth.
Yeah.
And that's what's creating either that, attraction or repulsion.
Precisely. It's a very mind-bending concept, but it's incredibly powerful. And it's not just electromagnetism. All the fundamental forces, the weak force, the strong force, and even gravity, although that one's still a bit of a puzzle. But they're thought to work through this exchange of these force carrier particles.
Okay, so QFT is giving us this new way of understanding particles and forces, but where does this, fit in to the bigger picture of physics?
So QFT is the bedrock of what we call the standard model of particle physics, which is arguably one of the most successful scientific theories ever. And it describes all the known fundamental particles and how they interact through these three forces: the electromagnetic force, the weak force, and the strong force.
Okay, so it's like the ultimate periodic table, but for the tiniest bits of matter.
Yeah, exactly. And it's really amazing that the standard model, which is built upon these principles of QFT, has been incredibly successful in predicting the existence of new particles, like the Higgs boson, which was discovered at the Large Hadron Collider back in 2012.
That was a big deal. I remember that.
Yeah.
It was like we found the missing piece of a giant cosmic puzzle. But even with the standard model, there's still some mysteries to solve, right?
Oh, absolutely. The standard model is amazing, a real triumph of human ingenuity, but it's not the final word.
Right.
There are still some major puzzles out there that QFT hasn't been able to crack.
Okay,
Like, why is gravity so much weaker than the other forces?
Yeah, it's a good question. I mean, gravity feels pretty strong to me when I trip and fall, but compared to the other forces, yeah, it's like a whisper in a hurricane.
Exactly. And this discrepancy in strength is known as the hierarchy problem, and it's been a major headache for physicists. It suggests that there might be something really fundamental that we're missing, something beyond the standard model.
Intriguing. So QFT has given us the standard model, which explains a lot, but it's also opened up a whole new set of questions, like new mysteries to explore.
And that's what makes it so exciting. There's still so much we don't know about the universe at its deepest level. But thanks to QFT, we have the tools to keep asking the big questions and pushing the boundaries.
Well, my curiosity is officially piqued. I'm ready to dive deeper into some of these mind-bending concepts. But before we go there, let's take a quick recap. So QFT has revolutionized our understanding of particles and forces, giving us the standard model and a whole bunch of new mysteries to explore.
Yeah. And the key takeaway here is that the universe is not made up of solid objects. It's actually made of these interacting fields. It's a dynamic, it's ever-changing, it's a tapestry.
It's a beautiful image.
Woven from the fabric of reality itself.
So, are you ready to venture further into the quantum realm?
Absolutely. Let's see what other wonders await us.
All right, listeners, hold on tight, because in the next part, we're going to unpack some of the most fascinating tools and concepts of QFT, including those famous Feynman diagrams. You won't want to miss it. Welcome back, everyone. Last time we dove headfirst into this really mind-bending world of quantum field theory.
Right into the deep end.
Yeah, exactly. Where we learned that reality is not really about solid objects. It's more about these invisible fields that are just permeating everything.
They're everywhere.
Yeah. And we even talked about how particles are like ripples in these fields.
Yeah.
But how do these particles like interact? How do they create the forces that we experience?
Right.
That's where we left off.
Yeah, that's a really fundamental question in physics.
Right.
And thankfully, QFT has some really cool tools for helping us visualize and understand these interactions.
Okay, so that's where like those Feynman diagrams come in, right?
Right.
They kind of sound like a secret code for physicists.
They might look like a secret code at first glance, with all their squiggly lines and symbols, but they're actually incredibly useful for representing particle interactions. Think of them as visual blueprints that show how particles exchange force carriers, like those virtual photons we talked about earlier.
Okay, so I'm picturing these diagrams almost like a comic book for particle physics.
Yeah.
Can you give us an example of how they work?
Absolutely. So imagine two electrons approaching each other.
Okay.
In classical physics, we'd say they repel each other because of their electric force or electric charge.
Right.
But in QFT, we see this repulsion as an exchange of virtual photons.
Okay.
So the Feynman diagram for this interaction would show two electron lines coming in, exchanging a wavy photon line, and then two electron lines going out, moving apart.
So the diagram shows how these virtual photons, these temporary particles, are like carrying the force between the electrons, making them repel each other. Exactly. It's like they're playing a game of quantum catch, but with these force-carrying particles.
That's a great way to think about it.
Okay.
And it's not just limited to electrons and photons. Feynman diagrams can describe all sorts of interactions.
Okay.
From particles decaying into other particles to the creation and annihilation of matter and antimatter. They're really this powerful visual language for understanding the quantum world.
It's fascinating how these diagrams can simplify such complex processes. But I have to admit, I'm still struggling a bit with this whole concept of virtual particles.
Yeah.
Like, if they're not directly observable, how do we even know they exist?
That's a great question.
Yeah.
And it goes to the heart of how QFT challenges our classical intuition.
Right.
So virtual particles are a consequence of something called the Heisenberg uncertainty principle, which tells us that certain pairs of physical quantities like energy and time can't be known precisely at the same time. This means that even in a vacuum where we'd expect no particles, there's this constant fluctuation of energy, allowing these virtual particles to just pop in and out of existence for these very, very short periods of time.
So it's almost like the vacuum is borrowing energy from the universe's bank, creating these virtual particles, and then quickly paying it back before anyone notices.
Exactly.
And these fleeting particles are what allow forces to act over a distance.
Right. They're like the messengers of the quantum world, carrying forces that shape the interactions between particles.
I'm starting to get it. So we've got particles, we've got fields, we've got these force-carrying virtual particles. But how do we know what rules govern these interactions? How do we know which particles interact with which forces?
That's where the elegant concept of gauge theories comes in.
Yes. Gauge theories. I remember you mentioned this earlier.
Yeah.
I was thinking, okay, this sounds complicated, but I'm ready. I'm ready to be enlightened.
Okay, great.
What makes these theories so special?
So gauge theories are based on this idea of symmetry.
Okay.
Think about a snowflake, for example.
Okay.
It's symmetrical, which means you can rotate it by a certain angle, and it still looks the same.
Right.
And in physics, symmetries are associated with conservation laws. For example, the laws of physics are the same whether you're in Paris or in Tokyo. That's a symmetry of space, and it leads to the conservation of momentum.
Right.
So how does this relate to particles and forces? In gauge theories, the symmetries aren't about space or time, but about these internal properties of particles, like electric charge.
Okay.
So the idea is that the laws of physics should remain the same, even if we make certain changes to our description of these properties.
Okay. Can you give us like a concrete example of that?
Sure. Take electromagnetism. It's described by a gauge theory called quantum electrodynamics, or QED.
Right.
And in QED, the gauge symmetry is related to the phase of an electron's wave function.
Okay, hold on. Wave function, phase. You're losing me a little bit.
You can think of it this way.
Okay.
An electron's wave function describes its quantum state.
Right.
And the phase is like an angle that can rotate.
Okay.
So in QED, we can change the phase of the wave function, kind of like rotating it, without affecting the physical observables, like the electron's charge or its interactions with the electromagnetic field.
So it's kind of like changing the orientation of the snowflake, but without changing its shape.
Yeah, that's a good analogy.
Okay.
And the amazing thing is that this gauge symmetry, this freedom to change the phase without affecting the physics, leads directly to the existence of the electromagnetic field and the photon as its force carrier.
Wow. So a simple symmetry principle can give rise to like one of the fundamental forces of nature. That's incredible. And I'm guessing gauge theories are also behind the other forces in the Standard Model.
You got it. So, the weak force, which governs things like radioactive decay, is described by a gauge theory called electroweak theory. And it actually unifies electromagnetism and the weak force into a single framework, showing that they're two aspects of the same fundamental force.
That's mind-blowing. So electromagnetism and the weak force are like unified?
Right.
What about the strong force, the one that holds quarks together inside protons and neutrons?
The strong force is also described by a gauge theory, but it's a bit more complicated. It's called quantum chromodynamics, or QCD.
Right.
And in QCD, the gauge symmetry is related to a property of quarks called color charge.
Color charge, like red, green, and blue.
It's not actually related to visual colors.
Okay.
But the analogy is helpful. So quarks come in these three different colors.
Okay.
And the strong force acts between them through the exchange of particles called gluons.
So it's like the quarks are playing catch with gluons.
Yeah.
And that's what's keeping them stuck together inside protons and neutrons.
Exactly. And the strong force is incredibly strong, hence the name.
Yep.
It's what binds quarks together so tightly that we never see them in isolation.
That's amazing. So we've got Feynman diagrams to visualize these interactions.
Yeah.
And we've got gauge theories to explain the rules of the game.
Yeah.
QFT is really starting to, like, come together.
Yeah.
But we're not done yet, right?
Not quite.
Okay.
In the next part, we're going to tackle some of the big mysteries that still puzzle physicists, like the hierarchy problem.
Right.
Dark matter, dark energy, and the ongoing quest to incorporate gravity into QFT.
Ooh, I'm on the edge of my seat.
It's going to be good.
Listeners, get ready for the grand finale of our quantum field theory deep dive. We'll be right back. Welcome back, listeners. We've been on quite a journey into the quantum realm, exploring this mind-bending world of quantum field theory.
Yeah, it's a wild ride.
We've seen how particles are like these ripples in visible fields.
Right.
How they interact through these force-carrying particles that are just, popping in and out of existence.
Sure. Yeah. It's a strange world down there.
It really is. And how this elegant concept of gauge theories governs these interactions.
Yeah.
But as with any great adventure, the deeper we go, the more mysteries we uncover.
Absolutely. And some of these mysteries are the biggest and most challenging in all of physics. They're the questions that keep physicists up at night, just driving that quest for a deeper understanding.
Okay, so spill the beans. What are these grand challenges? What puzzles are QFT still not able to solve?
Well, one of the most glaring ones is the issue of gravity. We've got this beautiful framework for describing three of the four fundamental forces.
Right.
Electromagnetism, the weak force, and the strong force.
Right, we've talked about those.
But gravity just doesn't seem to fit in.
It's like we've got this amazing party going on with QFT and the Standard Model.
Yeah.
but gravity's stuck outside, awkwardly trying to get in.
That's a great analogy. So Einstein's theory of general relativity describes gravity as this curvature of space-time. But it's a classical theory, meaning it doesn't incorporate the principles of quantum mechanics.
Right.
And when we try to quantize gravity to make it compatible with QFT, we run into all sorts of mathematical roadblocks.
You mean those pesky infinities popping up again?
Yeah.
Didn't we already deal with those in QED using renormalization?
We did, and renormalization is a brilliant technique.
Right.
But it doesn't quite work the same way for gravity.
Okay.
The infinities we encounter in quantum gravity they're much more stubborn. It's like trying to patch a leaky boat with duct tape when there are just holes everywhere.
So are we stuck then? Is there no way to unify gravity with the quantum world?
Not necessarily. Not necessarily. Physicists are incredibly clever and persistent. There are a few promising avenues of research, each with its own, unique approach and set of challenges.
Okay, give us some hope here. What are these approaches?
So one of the leading contenders is string theory, which, as you might recall, proposes that the fundamental building blocks of the universe aren't point-like particles. They're these tiny vibrating strings.
Right, like the universe is a cosmic symphony and the strings are the instruments.
Yeah, exactly. Exactly.
How does that help us with gravity?
So one of the really beautiful things about string theory is that it naturally incorporates gravity. One of the vibrational modes of these strings corresponds to a graviton, which is the hypothetical force carrier particle for gravity. It's like the string is playing a specific note.
Okay.
And that note is gravity.
That's really elegant. But isn't string theory notoriously complex and difficult to test experimentally?
It is one of the main criticisms. It requires these extra spatial dimensions, which we haven't observed yet.
Right.
And it makes predictions that are very difficult to verify with our current technology. But it's still a very active area of research, and a lot of physicists believe that it holds the key to a truly unified theory of everything.
Okay, so string theory is one option. What about the other approach that you mentioned?
So the other prominent candidate is loop quantum gravity, or LQG.
Right.
And LQG takes a different approach. It suggests that space-time itself has a granular structure at the Planck scale, which is the smallest possible scale in physics.
So instead of like this smooth, continuous space-time,
right,
it's more like space-time is made up of tiny building blocks.
Yeah, like a quantum Lego set.
Like a quantum Lego set. I like that. And this granular structure of space-time in LQG avoids some of the mathematical problems that plague the other attempts to quantize gravity.
Okay.
It's still a work in progress, but it has some very intriguing features that make it a serious contender in that quest for a theory of quantum gravity. It's just fascinating how these two theories, string theory and loop quantum gravity, are tackling the same problem, but from these really different angles. Like they're looking at the same puzzle, but they're trying to solve it with completely different strategies.
And that's the beauty of science. You know, we need these diverse approaches, creative thinking, and a healthy dose of skepticism to really push the boundaries of knowledge.
Absolutely.
Yeah.
But let's not forget about those other cosmic enigmas.
Right.
Dark matter and dark energy.
Yes.
These invisible entities are like calling the shots in the universe.
They are.
But we still have no idea what they are.
Dark matter and dark energy are perhaps the most perplexing puzzles in modern physics. So they don't interact with light, so we can't see them directly, but their gravitational effects are undeniable.
Right.
So dark matter seems to be holding galaxies together, preventing them from flying apart, while dark energy is driving this accelerated expansion of the universe.
It's like there's a whole hidden side to the universe that we're only just beginning to get a glimpse of. And QFT hasn't been able to give us a satisfying explanation yet, right?
That's right. QFT is incredibly successful at describing the particles and forces that we know about.
Right.
But it doesn't account for dark matter or dark energy. And this strongly suggests that there's new physics out there beyond the standard model, perhaps involving particles and forces we haven't even imagined yet.
Wow. So even though QFT has, like, revolutionized our understanding of the universe, it's also revealed how much we still don't know. It's kind of humbling, but also really exciting at the same time.
I completely agree. The quest to understand the universe is an ongoing adventure. And QFT has equipped us with these powerful tools, these profound insights to continue that journey.
Well, that brings our deep dive into quantum field theory to a close.
Yeah.
We've explored this strange and beautiful world of quantum fields, particles that just pop in and out of existence, and the elegant symmetries that govern the fundamental forces of nature. We've also encountered some of the biggest mysteries in physics.
Absolutely.
Mysteries that continue to challenge and inspire physicists all over the world. And remember, even though QFT might seem abstract and complex, its implications are far-reaching.
Absolutely.
It challenges our very understanding of reality, showing us that the universe is far more interconnected and dynamic than we ever imagined. So to our listeners, keep exploring, keep questioning, keep wondering. The universe is full of secrets just waiting to be uncovered. And who knows, maybe one day you'll be the one to make the next groundbreaking discovery in the realm of quantum field theory.